So, good morning, everybody, or good early morning, I should probably say. For me, it doesn't matter so much. I'm still very much jet lagged, so any time of the day feels similar to me. Okay, anyway, thanks for being here so early after the social event. We're going to be talking about planning. The first thing I'd like to say in this context is that the word planning was created in the early 70s, having in mind that planning is going to be the process that decides about the actions in an autonomous robot. That's how our area got its name. Now, as you can maybe guess from this picture here, so what it's trying to say is that planning and robotics were kind of co-created in a way, if you will. However, several decades went by then where, like, on one side we were busy, like, trying to figure out how to stack 3 blocks on top of each other, or at least that's a cliche, while the other guys were busy holding screwdrivers and trying to make the robots not keel over. Well, partly they're still busy doing that today, I think. Anyway, those things have changed, so both fields have matured. We've kind of lost sight of each other during the 70s, 80s, and 90s, and now we're trying to get back closer together, or at least part of us are. And so I'd be very happy if I can make a little contribution to this by speaking to you here. Okay, so this is the outline of the talk. First, I'm going to have a little motivation section. I'll try to go through that quickly. Brian has already said most of I think what I would be saying there. And then there's a technical part about the delete relaxation and beyond that. So there I'll try to, actually explain you some technical things, artifacts in our area. And then I didn't find a better section title for this, but those are some really cool ideas that I think you can apply no matter if you want to use planning or whatever else, so long as you're trying to solve this kind of problem. Then I'll be talking a bit about future challenges. Now, to get a gauge on you guys, who knows what classical planning is? Can you give me a hand? Okay, that makes it like a 30%. Who knows what the delete relaxation is? Okay, good. So I will be starting sort of like at the basics, like at the basement. I'll be trying to get into the upper floors within the 60 minutes I've allocated to this. So the 5 of you who already know what the delete relaxation is are going to be bored for a while, but I promise you're not going to be bored after 40 minutes or so anymore. Okay, good. Let's get right into it. Now, this seems a fairly technical start into a talk. I just wanted to give you some actual meat. This is what we guys are going on about since decades, more or less. Let us just look at an example to illustrate what the definition is. So this is the kind of problem we're trying to solve. Okay, what you see in the definition is how the problem is defined formally. Let's just look at the example. There's a vector of state variables describing the possible states in the world we're interested in the world segment we're interested in. We often use sort of logistics-style illustrations, but it's really just to give you the basic ideas, right? So imagine you have a truck and a package moving on some world map with locations A, B, C, D. You can model this in terms of 2 state variables, one given the position of the truck, one of the package. And those are finite domain state variables, so we're talking about the discrete world model here, okay? We just say the truck is at location A, B, C, D, not more than that. The package, same locations plus T, meaning it's currently in a truck. Then we can specify an initial state, which just gives values to the state variables that's hold at the outset, and we give a goal. Those are values of state variables we want to achieve at the end of the plan. Okay, the plan is a sequence of actions that take us from the initial state to a state that satisfies the goal condition. So you can think about the goal as a condition. Okay, so how do we specify the transitions? I mean, it's basically reachability in a transition system from a given start state to a set of end states specified by the goal condition, right? How do we specify the transitions? Via what we call actions. In this case, driving, loading, and unloading, and each action is specified by a precondition and an effect. So for example, if my action says load package 1 at location X, the precondition is that the truck is at location X, that the package is also at location X. So those things need to be true so that you can apply the action. The effect is what happens if you do apply the action, namely the package is now in the truck and everything else remains unchanged. So it's a fairly intuitive semantics, I think. Right? So it's just basically a compact representation of a transition system that you call the state space, and deciding whether there exists, like given, if somebody gives you a planning task like this, deciding whether a plan exists is a p-space complete problem. So this is a very general formalism, like we don't imply any restrictions on the form of the actions or anything. It could be really literally anything, ranging from Rubik's Cube to robots, okay? And in full general, solving this problem is p-space complete. Just to illustrate that this is not limited to trucks and packages, this is some work I did at SAP, like the German software company, where the planning model basically modeled the behavior of a whole IT infrastructure, and the planning process generated business process templates. This is some work other people have done. They actually use this to control printing machines, so the planner controls the printing machine. And the thing is that the customer may not just buy 1 out of 17 printing machines online, but may actually compose their own printing machine from a set of components. And then they use planning in order to create a controller that could control arbitrary printing machines, like out of the space of billions of printing machines possible. Okay, at this point I'm also gonna briefly go out of here. I had meant to do this later, but I think it's nice to do this now, actually. This is a directory I have on my homepage called Planning for Dummies. It's just sort of to give people who have never seen this before an impression. I've changed to a directory called Myconic ADL. This is from an elevator control application of planning. And this is the actual surface language we use to describe planning problems. It's called Pddl. Is there going to be some Pddl modeling in the lab exercises, actually?
The lab 3 will focus on Pddl modeling.
Okay, great. So you're going to write this kind of stuff later today yourself. So like I said, this is from an elevator control application. So the planner controls like how the elevators go up and down. This here is what we call a domain file. So all of this is rooted in logics, right? Classical AI. There are predicates that describe the states. Those will later turn into the state variables. We don't need to go into the specifics of this, but there's predicates to describe the state, okay? For example, the origin of a passenger, the destination of a passenger, which floor is a bunch of other one, which persons are currently in the lift, and so on. Then there are action descriptions. So this is an action. It has parameters. So it's a parameterized action. We also call this an action schema. I will get back to this later on. Then it has a precondition, and in general, the precondition can have pretty complex formulas. In case in question, actually, the elevator company Schindler Lifts contacted us because they were unable to write this kind of thing themselves, as you might sort of understand or appreciate when you see this precondition. Why is elevator control so complicated? Well, they had sorts of side constraints, like, for example, there were groups A and groups B of people who should never meet inside the elevator. I'm not sure what the intended application of this is, but anyway, so there is an action that basically says stop at the floor, and obviously the elevator can't take people and put them in and out of the lift, right? The underlying assumption is that whoever has the destination is going to get out, whoever is not the destination is going to get in. So this is what this effect specification is saying. All passengers that are not yet boarded and that have their destination, that are boarded and have their destination are going to get out. Okay, and then there's up and down action, just move the lift. But I mean, really, the only thing I wanted to show you is this is what the language looks like. This is how we specify the predicates and action schemas that hold for the entire domain. Like for any elevator control task, these are going to be the predicates and actions. And then there's another file called the problem file that gives the actual object universe. So there's a finite universe, and here we specify what it is. In this case, there are just 2 passengers and 5 floors, so it's a tiny elevator control problem. Then you give the initial state, and then you give the goal. Okay, so there's a distinction. This here changes for, like, if you have 17 passengers or 27, you have a different problem file. So any one domain has a possible infinite set of possible problem files, but the predicates and actions always stay the same. Okay, I'll get back to this kind of stuff later on. I just wanted to briefly give you an impression of what this looks like. So the tools we build basically pass this complex language, and then they, run search algorithms in order to figure out what a plan could be. Good. Back to robotics. So, I mean, this already kind of tells you, right? I've talked now about software control and business processes. I've talked about controlling printers. I've talked about controlling elevators. In my own work right now, I'm using this kind of stuff for language generation and for automatic security testing. So it's a very general approach. You can do all sorts of things. It's not limited to robotics, if you will. But what we're talking about today is robotics. So let me try to motivate you guys why it could be relevant for this. This is basically what happens when your robots follow scripted workflows, right? Like fixed processes. Like you could think of houseflies as following a very stupid scripted workflow, at least in certain situations. I mean, they have survived for quite a while, so it can't be that bad. But they're unable to get, out of windows, like when evolution created them, probably there weren't any windows just yet. So not scripted in the workflow. This is what happens when you use planning, right? Sort of like you sense what's going on, and if something is not as you expected, you can actually replan and do something else, rather than just banging your head against the wall. And that's what Brian already talked about yesterday, so I'm not going to dwell on this. But essentially, planning is a method to, create a high degree of flexibility if you're trying to build a system that acts autonomously in this world under dynamic changing circumstances that you can't all foresee at design time. It's sometimes very hard to model, foresee, and plan for, like fix a decision for everything that could happen out there in the world. So if you just think about even in autonomous driving, it's pretty difficult. Okay, so let's assume that you want to put this planning process inside like the heads, the decision control of a robot. What would you want this thing to be able to do? I mean, there's not just one planning. Planning is a highly ambiguous word. There's like books this thick on just explaining all the different variants of planning. Okay, so let's look at the dimensions a little bit. We can look at discrete world model versus continuous, right? We could look at instantaneous actions or ones that take time, right? Like, I mean, actions differ depending on how much time they take. Flying from Frankfurt to Boston takes longer than flying from Washington to Boston. We can talk about sequential plans where all the actions are just one after the other, or concurrent ones, like we all flew to the school pretty much concurrently. We can talk about observability. Do I know everything in the world, or do I know only part of it? Determinism, so if you throw a dice, it's not a deterministic action. If I go from here to there, I could pretty much say it was a deterministic action, right? I knew a priori before I executed the action that I'm going to end up there. There was no stochasticity or anything like that. Okay, finally, you might talk about plans that just achieve some condition at the end, or plans that actually have to satisfy more complex temporal preferences or constraints. If you think a little bit, this is actually often the case. So now, I don't know, so who of you are roboticists or trying to, who of you are working on robotics? Can you give me a hand? Okay, so probably when you're looking at this table here, you think what you want is the red things, right? Like you probably want your robot to be able to deal with all of this. So here's the semantics of red and blue, right? Okay, so at this point you're welcome to leave the room if you so wish. So why is this relevant at all? Well, I mean, I told you planning is a piece-based complete problem. I mean, acting flexibly in an arbitrary world. I mean, we might argue whether this level of generality is actually needed, and I'm happy to talk about this, and I think the answer is certainly no. But okay, for the time being, it is very difficult to find middle grounds between this and that. If you restrict the syntax a little bit, you end up with trivial languages in which you can't describe your problems anymore. And if you actually want the red parts, it gets like, blastingly difficult, like impossible to solve even tiny problems. So what classical planning gives you, well, it's not very expressive in this sense here, but it's still quite expressive in the sense that you can model a broad range of problems, and it's fast, like relatively speaking. We got mature algorithmic methods to solve this kind of thing. So there's actually a hope you can put this into your robot and get replanning that is fast enough to act in the real world, without standing around for 7 hours and just, I mean, usually you don't have time to think for a very long time out there in the world. Okay, the other thing is that this is basic research, right? I mean, I was introduced as saying this, okay, it's going to be a foundational talk, and that's what it is. And the good news is that many of the ideas, it's a good framework to be developing algorithmic ideas, and many of those have later on been transferred to more expressive planning models that are probably closer to what you need on actual robots. So for example, what I'm going to be talking about is pretty straightforward to extend to temporal and concurrent planning. That's pretty easy. Some of the other dimensions are more difficult. Okay, I mean, I should say, relatively speaking, easy, right? It's not like this is trivial. People are writing papers about this. Okay, algorithms, right? Foundational research, good. There's, of course, a broad range of ways how you can solve this kind of problem. I'm going to be talking about one way that's been particularly successful in the planning community for reasons that we're not going to get into the detail of here, but certainly this is one promising approach. Heuristic search is pretty simple. Forward search, you start at the initial state and you just keep expanding actions to reach new states until eventually you reach the goal. Okay, so a priori this could just be like Dijkstra in a graph. The problem is the graph is very big. Like if your planning task is this big, the graph will go like from here to the ceiling. I mean, it's exponentially large in the size of the input, right? Actually doubly exponential if you think about the Pddl we saw before. So we can't search this whole graph. It's just not possible in all but the tiniest example. So we're going to need some sort of guidance. Heuristic search. Who knows what heuristic search is? And I can stop blabbering about it. Almost everybody. Okay, well, you have this function, h, that maps states to an estimate of goal distance, and then you just go wherever the heuristic function has the smallest value, where you seem to be getting closer to the goal. This is a whole sub-area of AI, but I'm going to leave it at that. What I'm going to be talking about more is how to generate the heuristic functions. So the thing is, I've shown you this huge Pddl thing. Imagine you're writing a program that has to parse all of this, and now you want to run this algorithm, but where does the function h come from? Right? You know, it's not there. People, the guys haven't given it to you in a model. All you're getting is a description of the world. You have to turn this world description into the function h. How do you do this? Fully automatically without getting any help from a human. So like the classical paradigm is there's a human programmer who programs this function, end of story. In planning, you have to create this from the model. Now, the basic principle is always the same, like whether a human or a computer does it, so-called relaxation. So for example, if you have this problem here, a relaxation is just a simplification of the problem that throws away some of the constraints. For example, I could pretend that I have a helicopter and I don't need all those roads and ships and shit like that, right? I can go in a straight line. The optimal solution to the relaxation is then the straight line distance, which is obviously a lower bound on the real cost I'm going to have to pay to get from here to there, right? So you have a problem, you relax it, you solve the relaxed problem optimally, you get a lower bound on the real cost of solving the problem. That lower bound is going to be your function h. And then the whole question is how to do this given just the Pddl model. So how do you relax the problem? How do you solve the relaxed problem? Okay. And I don't know if this sounds boring to you, but this is what has kept us occupied since about 97 in a substantial fraction of the planning community. So it's not as easy as you might think, or I don't know if you think it's easy. There has been a couple of interesting ideas coming out of this research. I'm going to talk about a few of them. So I'm going to talk about the delete relaxation because it's a canonical and very simple method. It turns out to be very effective in practice. Then I'm going to be talking about the pitfalls, the weaknesses of this technique, in particular sort of weaknesses relating to robotics and how to fix those. And then I'm going to be talking about some other cool stuff. Basically just throw some ideas at you that I think are nice. Good. The delete relaxation. Intuitively speaking, this is what it does. It pretends that nothing ever becomes false. So in the real world, for example, imagine you're buying a car. Before you buy the car, you have the money. Okay. After you buy the car, the other guy has the money. That's bad, right? I mean, you got the car, but you don't have the money anymore. If you do this under delete relaxation, before you buy the car, you have the money. After you buy the car, the other guy has the money, but you also still have the money. Okay, so the money has doubled as part of the process of buying a car. So that's kind of nice if you think through the implications, right? You need to earn a salary just once, and then you can live on that for the rest of your life. So it's quite convenient. So it's a very strange world, right? If you drink a beer in the real world, afterwards it's empty, as you've probably noticed at some point or other. Under delete relaxation, you drink a beer, afterwards it's empty, but you also still have the beer. So you can just keep drinking it. Okay, and all sorts of other things, like, so it's a strange world in delete relaxation. Remember, this is not what you're trying to solve. I mean, pretending that you have to earn just one salary and then, do whatever, like fuel up your car once and drive across the whole world just on that one tank. It's not going to work, right? In delete relaxation, it works. Remember, this is only something we do inside this function h here, right? All of this happens inside this thing here, and the search doesn't care about what it is. It just takes back the number and uses it to search in the actual problem. Okay, some people in my lectures even confuse this still at exam time, so that's why I repeated it just now. Okay, good. So this is what it does. A little more formally, or first, basically the intuition again, I guess. It seems a bit strange that those two facts can coexist. Yes, please.
So how is delete relaxation related with edge separate?
With edge what?
With heuristic function.
Okay, you compute a plan that solves the problem under this relaxation, and then you just take the length of the plan and give back that length as the number. But we're going to get it into this on the next slides. Yes, it's one possible way you can relax the planning task and then get a heuristic value out of that, yes. We got like 5 families of heuristic functions at this point. This is one of them. Okay. Okay, good. So a little more formally, Well, okay, what I wanted to say before the question was that those two facts coexist, so it's a bit of a self-contradictory world. Now, the reason why this is making this problem simpler over approximating, being optimistic, is that you can choose whichever one you like better, right? So if you like the empty beer better, you can use that. If you like the full beer better, you can use that. Or if I drive a truck from A to B, afterwards it's at A and B simultaneously, and you know, whichever one I like better, A or B, I can use. I'm free to pick which one I can use. So that's why it's an optimistic approximation. Okay, a little more formally, these are state transitions in the real planning task, right? So you go from a state S to a state S prime by applying an action, and S prime of a state variable is going to be the effect of the action where defined, and the previous state otherwise. So this is just how state transitions are actually defined, and this is how we relax them in the delete relaxation. Just look at the red parts, don't bother reading the actual definition. So the state is now just some set of variable value pairs. It's no longer an assignment to variables because the same variable can have several values simultaneously. Okay, so each variable is mapped to a subset of its domain. And then I can apply an action if all of its preconditions are true somewhere. And the new state is just the old state plus the effect. So I don't overwrite the previous state, I just take the previous state and put all the effects into it as well. So the state just keeps getting larger and larger, more and more facts become true. Okay. Well, I haven't previously actually talked about the goal in this example. Well, that's not important. Let me just skip over this. Let me show you this other example here. Imagine you're working in a circus and there are these tigers that you need to make jump through rings on fire. So interesting job. You also want to be alive at the end. So this is like a simple encoding of the planning problem. Initially you're alive. Your goal is that the tiger has jumped and that you're still alive afterwards. These are the actions. You can get a tiger, you can tame the tiger. And then there's two versions of jump. You can make the tiger jump without taming it a priori, or you can make the tamed tiger jump. So in this variant here, the tiger jumps, but afterwards you're not alive anymore. Question, what is the relaxed plan for this task? A delete relaxed plan for this task. So I guess you can see what the real plan is, but what is a relaxed plan for this? Yes? Sorry, the guy in the back? Just jump tiger? Well, you have to get the tiger first, right? So then you have the tiger, then you can jump, yes. So get the tiger, jump tiger. Why is this a plan? Can you elaborate? Why is this enough? Pardon? Okay, still not sure I got you acoustically, but I mean the point is that you don't have to tame the tiger first, right? You don't have to use this action because while this jump tiger here makes you not being alive anymore, you don't care. It's delete relaxed, right? So you've been alive before, so you're still alive afterwards. You're also not alive, but who cares? You can pick whichever effect you like better being alive, so that's it. This here would also be a relaxed plan, but this one is shorter. So this already shows you like pitfalls of delete relaxation, right? So if actions in your task have detrimental side effects, like jumping off a cliff has the side effect of being dead, delete relaxation is not going to notice, right? If jumping off the cliff has a beneficial effect, if you want to be at the bottom of the valley, it's just going to jump, right? So then the length of the plan is 1, jump off the cliff, whereas the actual plan would, you know, require walking way out there and finding a staircase down to the bottom of the valley, right? So as far as the algorithm is concerned, it's just a bad lower bound in cases like that. Okay, good. So this is how the delete relaxation works. That's the mechanics. We were talking about heuristic functions. Do you have a question? Yes.
In the previous question, the goal was to have it alive, right?
The goal is to be alive and to have the tiger jump. Yeah. When I do jump tiger, I'm deleting the goal, yes, so this is a negation, right? That's correct. So this plan here doesn't work in reality. However, it works under delete relaxation because if you think through the states here in, right, initially you're alive. Okay, I get the tiger, now I'm alive and I have the tiger. Now I do this. Okay, now I'm alive and I have the tiger and I have the jump and I'm not alive. Okay. But alive is just one state variable, right? It's a Boolean state variable. It's 2 possible values, like 1 and 0. Initially it's 1. So here it's still 1. This action sets it to 0, however, under delete relaxation. Remember this definition here. I take the previous value of the variable 1, and I take the set union with the new variable, with the new value 0. So now the variable has two values, 0 and 1. And I'm free to pick whichever I want. Okay, so now this alive variable has accumulated both its values, and I'm free to pick whichever one I'm happy with. Okay. Good. So the definition of the heuristic function, I mean, we want to talk about the actual lower bound. It's called H+, and it's just the cost of an optimal relaxed plan for a state. So on any state during the search, you're going to solve this delete relaxed problem optimally, okay, and then you're going to take the cost of the optimal relaxed plan as your lower bound on goal distance. So now we're back in this picture here, right? So you're running the search on, let's say, this state here. You just, put this state into the delete relaxation, solve it optimally, and just take the cost of that plan and use it as the value in your search. Okay. Sorry, wrong slide. Good. So, the good news is that this is actually a lower bound. I'm not going to dwell on this. I mean, it's an optimistic relaxation. If you solve it optimally, you get a lower bound on the real cost. Another piece of good news is that this often gives very informative lower bounds, like, informative search guidance. Here's one example. Let's say you want to visit this continent. You're initially in Sydney. Okay, for some reason I don't visit Melbourne. Any people from Melbourne here, my apologies. How do I solve this under delete relaxation? Well, first of all, I can drive the truck into two directions at the same time, right? And afterwards I got 3 trucks, like initially I'm in Sydney, I drive from here to here, I'm in Adelaide and Sydney. And if I also do this, I'm in Adelaide, Sydney, and Brisbane all at the same time. Okay. Now to visit the remaining 2 locations, I can just do this, and now I'm done, right? I've visited all locations on the map. Question to you. This is a very well-known lower bound for the TSP, the structure we've just built. Does somebody know what it is? Yes, exactly. That's the minimum spanning tree approximation. So that's certainly not the best known approximation for TSP, but it's a fairly reasonable one. And the point is that we can create this fully automatically. Right? So if somebody throws a Pddl model at me that describes TSP, and that's easily possible, right? And I apply this totally generic relaxation technique to it, what comes out is the minimum spanning tree approximation. It doesn't require any human input. Right? If you throw another Pddl problem at me, some other approximation will fall out at the end. So we can recreate this approximation of TSP fully automatically. That's the part that's interesting here. Okay, now there's been good news, so naturally there will be bad news, right? Bad news is that you can't actually do that. Computing this heuristic function is NP hard. So if you wanted to do this, you would have to solve an NP hard problem on every search state. Right? So again, back to this picture here. So every state you're creating, and remember the graph has billions of nodes, right? For every one of those nodes that you explore, you would have to solve an NP hard problem. Okay, certainly not something you want to try doing while your robot is standing around in a dynamic environment. Okay, the proof is very simple. I'm going to skip over this. So we approximate, okay, this is like, well, not a famous quote, but this is sort of like a quote you hear in almost every ICAPS talk, right? Hard problems are everywhere, so we need to approximate. Okay, how do we approximate H+? First attempt, and that's the first attempt people have come up with back in 99 or so. Let me put on this here already. Okay, regression. Who knows what pre-images are? Yeah, some people. Okay, so let me take you through this briefly. Let's first look at this equation here. It's basically formulating the cost of solving a planning problem in terms of a backward reasoning process. So this is your goal, this is your state. If the goal is already true in the state, then the cost is 0. That's the induction base case, so that's easy, right? Then there's the case where the goal has size 1. Okay, so your goal contains a single variable value that you want to achieve. What you then, well, you minimize over all actions over which this goal can be regressed. So this intuitively just means this action can achieve that goal. So you look at all actions that can achieve that goal, you minimize over them because you want a minimum cost plan, okay? And then you just take the cost of that action plus recursively the cost of achieving the precondition of that action. So this term here basically evaluates the precondition of the action. The regression of a goal over an action is the condition you need to achieve prior to the action, so that after the action your goal is true. This here is the formal definition, but I don't think I need to take you through this. Just, try to get this intuition here. If I just applied those first two cases, 0 if my goal is true, otherwise minimize overall actions that can achieve the goal. If I just apply those two, I get the exact plan cost. This simple function defines the exact plan cost because that's exactly what plans do. Now, why do I restrict this to singleton goals here? Because I'm not trying to compute the exact plan cost, which would be p-space hard. What I'm actually doing is approximating it. How do I approximate it? Well, by doing the real computation only on singleton goals, and if the goal is non-singleton, I just pick the single most costly goal in the set. So if I have a larger set, 17 goal facts to achieve, I just pick the single most costly one and take that to be the approximate cost of achieving the entire set, which of course is an under-approximation, it's the lower bound, right? Achieving a single goal is always easier than achieving the 17 goals. Okay, this is what this does. It doesn't really look like the lead relaxation heuristic at first sight, right? Where does the lead relaxation actually come into the play? Well, it happens that on singleton goal facts, regression ignores negative side effects intuitively. If you have 17 goals and you pick only a single one of them, then the action you use might be deleting like 12 of the other 16 goals, but you don't care, you don't see it because you're only considering this one goal right now. Okay. So this is a lower bound on H+. Okay. So we know that H+ is a lower bound on the real cost. It's an admissible heuristic. We know H1 is a lower bound on H+, so therefore H1 is an admissible heuristic function. It's a lower bound on the real plan cost. Okay, next question, how do we compute this? I'm also going to be quick on that. It's basically a simple forward table-like computation. So you start in the beginning in iteration 0 with value 0 for those things that are already true in the initial state and infinity everywhere else. Then you just keep chaining forward and see what you can reach. So at time step 1, I basically see, okay, the truck can already be at A. There's an action that takes me from A to B. Therefore, in the next step, I can be at B. And that has cost 1 because applying the action drive from A to B has cost 1. Okay. Next step, I can be at C. Next step, I can be at D. Then because the truck, the truck here could be at C, and the package can already be at C. So then in the next step, the package can be in a truck because I can load it. And we just keep chaining forward until the values stabilize, so until we reach a fixed point, and then from this we can read off the H1 heuristic value, which is just the maximum value in the last row here. So basically in the last row, in the fixed point, you just look at the goal facts. In our case here, we have 2 goal facts. Truck needs to be at A, has value 0. Package needs to be at D, has value 4. We take the maximum of those 2 values, 4. Okay, now if you think about this task here, you should transport the package from C to D and then drive the truck back to A. It takes like 1, 2, load 3, drive 4, unload 5, 6, 7, 8 steps, 4. It's not such an unreasonable lower bound. I mean, you are underestimating, but it's sort of okay. The point about H1 is that it's very much not okay as soon as you go to less trivial examples. So let's imagine we transport not 1 package but 100. It's the same task, it's just here you got not 1 package but 100. Okay, the real plan length is gonna be, 2 drives, 100 load actions, 1 more drive, 100 unload actions, drive back. So it's gonna be something like, 200 plus. Okay, what is the H1 heuristic value for this extension of the task? What if I have 100 packages? What will the lower bound be? So remember, all you're doing is going to this last row here, look at all goal facts, and pick the one with maximum value. So you think the lower bound is going to be 100? Somebody said that? Not the correct answer, it's less than 100. 4, exactly. Why 4? Do you want to explain? Because you care only about 1, it's not entirely true, so the goal would also be extended. There would be 100 packages that also have a goal, each of them, every one of them. However, the table is going to be symmetric. I mean, the last, these are the columns pertaining to the packages. The columns for all the other packages are going to look exactly the same. Now you go into the last row and you take the maximum over the goal fact, which is 0, 4, and then 4, 4, 4, 4, 4, 4, 4, 4, 4 for all other 100 packages, so the result is going to be 4, which is incredibly bad lower bound for this task. Intuitively, okay, you're approximating the goal distance by taking the single most costly goal. If you have 100 goals that all cost the same, it's going to account for only one of them and ignore the 99 others. So it is a lower bound, but in most typical practical examples, it's a very, very bad lower bound. It's very uninformative. So how do we fix this? Well, it turns out, and this is like the famous delete relaxation heuristic, it turns out we can use this function, h1, and instead of just returning its value, use it in order to extract a delete relax plan. So we can read off a delete relax plan from this function, and then just take the length of that plan as the estimate, and that fixes the problem I just outlined. How do you do this? This is just sort of backward relaxed plan instruction. So let me illustrate it here. You build this table as before, then you go into the last row, and then instead of just reading off the value, like instead of just reading off the value 4 for the goal package D, you look at the actions that achieve that fact. And then you say, okay, I'm going to have to use this action. So for example here, in order to get the package to D, what action do I have to apply? How do I achieve that goal? Unload the package at D, right? Okay, now unloading the package at D has preconditions that are now need to achieve recursively, right? The preconditions are the truck needs to be at D, so this here becomes a goal in the previous step, and the package needs to be in a truck, so this here also becomes a goal in the previous table row. I'm really just sort of chaining from the bottom back to the top table row, selecting actions and marking preconditions as new sub-goals. So here I got those two sub-goals, I need to achieve them. In order to get the truck to D, I need to drive from C to D, so this is my new sub-goal in the next step, right? In order to get the package into the truck, I need to load the package. Where do I load the package? Which location? Do you have a preference where to load it? I could load it at any location, right? I could load it at A, B, C, or D. Which one do you want? C. Why do you want C? Pardon? Yes? Yeah, the package is available at C. So if you look here, there are 4 possible actions to get the package into the truck, but only one of them has a precondition that can actually be achieved in this table row, namely being at C. So in this table row here, which is the one we need, the package isn't anywhere except at C, so the only action we can use is load at C. And then loading the package being at C becomes a new sub-goal here, which is already true, so we don't need to do anything about it, we just need to backchain from the truck being at C. And when we do all this, we get a relaxed plan for the task. Okay, the set of actions we collected at the end is a relaxed plan for the task. Okay, and now I'm going forward over all this. We don't really need, this is what I just explained on the slide. I made it a little faster for you, but I hope you get a rough intuition, right? Sort of chaining from the bottom row to the top row, selecting actions. The heuristic value here will be 5, okay? So the actions you're going to select, let me show you the, example. It looks like this, right? Here we have the illustration. The actions you're going to select are the following: drive from A to B, drive from B to C, load the package, drive from C to D, unload the package. 5. Okay. What is the part that we ignore? Like, what do we additionally have to do in the real task? One of our goals is for the truck to be at A, So I've now driven over here, unloaded the package. What am I missing? I'm not driving the truck back. Why do I not need to do this? Because it's true in the initial state, and in the delete relaxation, everything is still true. So once you've driven the truck from A to D, the truck is on the whole map simultaneously. You don't have to drive back anywhere. Okay, good. So the value is 5. It previously was 4. So this is like not super exciting, right? I mean, okay. It's closer to the real value 8, but the exciting part is this here. What happens if I have this extended example again? Now I have 100 packages. Okay, let's go back to the illustration. Now I got the same thing, but here we have 100 packages instead of 1. What are the actions that the relaxed plan is going to select? Well, it's still going to drive the truck from here to here, so much is clear. What it's going to do about the packages? Yes? Yes, it's going to load and unload every one of the 100 packages, and so you're going to get an estimate of 200 plus, which is much closer to the 200 plus that the actual plan costs, right? So by this very simple operation, we fixed the problem that we previously had in H1, and that's what makes this a very good heuristic. I was even able, like, it's already 15 years ago or something that I did this work, I was even able to attach a formal semantics to the words a very good heuristic. It's in this table here. I'm not going to explain in a lot of detail. Let me just say that in all those domains down here, I was able to prove that the H plus heuristic, the optimal relaxed plan heuristic, the one that's NP hard to compute, doesn't have any local minima. So you get a search-based surface that doesn't have any local minima in it, which is pretty much unheard of. You know, anytime you use heuristic search, all people are going on about a local minima. They actually don't exist here. If you're interested in this kind of stuff, you know, read the paper. But I'm going to skip over it here now. So the upshot is that this is a very good heuristic function. This table here talks about H plus. HFF is similar, basically. Okay, so it's a very good heuristic period. And that was the good news. And of course, there's also a bad news. Okay. So the bad news is that HFF can be located, well, it's generally located on the right-hand side of H plus. My favorite blackboard illustration is this. Heuristic search researchers basically live in this spectrum here. So this is where my life has taken place the last 25 years, between 0 and H star. Right? 0 is the nil heuristic. You can always return 0 and it's going to be a lower bound. H star is the real goal distance. Any heuristic you're going to design is going to be somewhere here. Okay, simple question to you guys. Are the endpoints of the spectrum any good? Does the 0 heuristic help you in the search? Yes, it doesn't contain any information, therefore it can't help you. What about H star? It'd be great, no? You have the exact distance to the goal. So you're not going to have to do much search, presumably. So is H star a good idea? Yes? If you want to have H star, you got to solve the problem inside the heuristic function. So, you know, it's nonsense. You know, in order to compute this function, you have to solve the problem in the first place. So the two ends of the spectrum are nonsense. The interesting points are in the middle of the spectrum. Now what this result is telling us is that H plus is somewhere here, H1 is somewhere here, and H of F is somewhere here. Okay, so H of F is not a lower bound on H plus. This per se could be okay. However, H of F can also end up down here. Okay, it can be larger than H star. It's not a lower bound anymore. Okay. Proving that it is not in general a lower bound is something you can do at home if you really want to think about this kind of stuff. It's a nice little thinking exercise. The problem is you cannot use this for optimal planning anymore. If you want to prove optimality, you need a lower bound. Okay, it's not a lower bound. You can only use it to find some plan about which you cannot give a guarantee. It's for what we call satisficing planning. Okay, good. Yeah, are there any questions at this point? Okay, so what's nice about this is, I mean, you can use it for optimal planning, but in many applications you don't need to. You know, often you don't care that your robot acts optimally. You want it to be able to actually act, you know, under the given time constraints and do something useful. And that's something you can definitely use this kind of technique for. And what's also nice is it's extremely simple. I mean, people have extended it in all sorts of directions because it has very good performance and it is very simple. It's a very canonical thing to be using if you want to extend it into whichever direction you care about. That's why I talked about it. Nevertheless, of course, it has pitfalls, and we're going to be talking about this next. So this is much closer to the state of the art. This is like work we've done like just 2 or 3 years back and that we're still working on. Okay, what I like to call partial lead relaxation is the following. So there's this gap between H plus and H star, right? So H plus tends to be a very good lower bound. I already told you that. However, there's a gap, and then of course, being researchers, we ask ourselves, okay, what can we do about that gap? Can we do better? Can we get inside this area here? And that's what partial lead relaxation tries to do. Okay. So partial lead relaxation means you should have some kind of interpolation parameter that enables you to navigate this whole distance between H plus and H star as a function of how you choose the parameter. That's what ideally you would like to achieve, like a systematic way of going beyond the lead relaxation and approaching real planning more accurately. Why would we be interested in doing this? Well, I've already showed you this tiger example. Of course, it's rather artificial, right? Things people care about more in practice are, for example, resource consumption. I mentioned this briefly. Under delete relaxation, you know, fueling up your car just once allows you to drive across the whole world. Think energy consumption, I don't know, in space. You know, you have a satellite with a limited battery. Under delete relaxation, you know, you could be photographing the whole universe and never run out of energy. It's stupid, right? So if energy consumption is important, delete relaxation is not going to help you, right? It's going to lead your search into directions that it thinks are useful, but it may turn out to be actually fatal, deadly, because you run out of energy at some point. And delete relaxation heuristic function hasn't noticed. So that can be really bad. Another thing is moving to and fro. Like, you know, in this real world here, usually we don't just go in one direction. We also have to go back at some point in order to get somewhere else. Like, think logistics. Or think a robot. You know, the location of a robot is not something that accumulates over time, right? The robot is only in one place, and it's quite normal that the robot is going to have to go back at some point. And delete relaxation just doesn't account for this kind of thing. It pretends that once the robot has moved through the entire building, it will always and forever be in the entire building at once. Just pick a coffee in the basement and give it to you right here in your office without having to move in between. So that's certainly not very useful approximation behavior. So what can we do about it? Here's an example I'm going to be using here to illustrate what's to come. Just to briefly explain the example, well, you're here initially, the packages are out there, you're going to have to take them all and transport them back to the central location. Okay. In the relaxed plan for this task, what you can do is, you know, I mean, in reality, you're going to have to drive from here to here, take the package, drive back. Go from here to here, take the package, drive back. Here, back, here, back. So I've said the word back 4 times, and those 4 occurrences of driving back are not going to be accounted for. Okay? If you do this with 100 packages, I'm going to say the word back, driving back 100 times. None of those are going to be accounted for. Now, how can we fix this? And this is the method I will be talking about. We called it red-black planning. Maybe I should apologize for the name. We were smoking a cigarette and thought this was funny because we were also talking about graphs, and then we had the red-black graphs, and we thought it was just hilarious. So the black variables, okay, let me start with the red variables. This here is the state transition function. This here says V is in the red variables. And that's the state transition functions I've told you about in the delete relaxation. You take the previous state, set union with the action effect. The difference now is that we're partitioning the state variables into the black and the red ones, and the black ones retain the original semantics. So if you apply the effect of an action on a black variable, you just get the effect of the action. What you had before is overwritten, like in the real world. The truck is no longer at A, it's now at B. Okay? Whereas for the red variables, we accumulate values like in delete relaxation. So you get a hybrid, right? You partition the variables into 2 parts. The black variables are treated under the real semantics. The red variables are treated under the relaxed semantics. That's all this definition is saying. You can already sort of do the simple maths and figure out that this is, can interpolate between relaxed and real planning, right? To make sure we're on the same page. How do I get H+? How do I have to choose the set of red variables to get H+? Yes? Somebody said something, if you can just say it again. I'm old, right? I'm half deaf, so you have to speak loudly and clearly. Yeah? Yeah, just choose all variables to be red. You're here. How do I get to this end? I choose all variables to be black. How do I navigate in between? Well, by choosing something in between those 2 extremes. Okay, so it's like, it's so simple. I mean, I'm still sort of flabbergasted that it took us like 12 years to come up with this definition. I mean, it's really like, what have you been thinking? Anyway, the reason why I'm talking about this is that, well, to some degree at least, it can be helpful in robotics, like better than delete relaxation. Why? Because you can, for example, paint the robot location black. Like the robot location is a state variable. If you make that black, then you are going to account for the fact that the robot is going to have to move forwards and backwards, back to the same locations quite often. And actually this team here who won some prize a few years back in the RoboCup at work are using our planning system based on red-black planning. So it's actually been put to use. Well, we could discuss the reasons for that, but never mind. Anyway, so it's certainly one useful way of fixing the problems of delete relaxation that can be relevant to robotics. Good. Illustrating an example. It's pretty simple. So let's say we paint the truck black, right? So this is the terminology we've been inventing here. So you take a state variable, you can paint it one of two colors. If you paint the truck black and the package is red, what's going to happen? So previously we noticed that, well, the truck, doesn't have to drive back in relaxation. Let's try to fix it. How do we do that? Well, we paint the truck black. It's not a relaxed variable anymore. It has to take the real semantics. Now let's try to apply the relaxed plan. Okay, first the relaxed plan tells us to drive from G to A. That's just fine. Then it tells us to drive from G to B. And at this point, it already breaks, right? Sorry, can't do this anymore under my more refined relaxation, because in order to drive from G to B, I would have to be a G, but I'm not. Right? In the relaxed plan, at this point, I was at both G and A together. Now I'm just at A. Doesn't work. So this is good news, right? The previous relaxed plan, which was bad, which was like a very spurious solution, has now been cut off from the solution space. That's good news. Question is, what does this solution space look like? And if you think about this a little bit, you will see that any optimal red-black plan is a real plan here. So actually just painting this one variable black has turned totally fucked up approximations into exact planning. Let's try to see why this is the case. And I usually like to explain this by asking, how can red-black plans go wrong here still? I mean, you can still produce red-black plans here that are not going to work in reality. Can somebody tell me how to do that? What can still go wrong under this more refined relaxation? How can the red-black plan still, well, cheat? Cheat is perhaps not the right word, but do something that you wouldn't be able to do in reality. The packages are still red, yes? Yes, the packages are red. You can drop off the same package over and over again, or you can load it like 3 times in a sequence, and nobody would care, right? So I could drive down here and load package A 17 times in a sequence, and that would be a valid plan, red-black plan, right? Because the package is red, after loading it, it's still here, so I can load it again and again and again and again. I can drop it off at the goal, and then without loading it again, I could also drop it off here and there. I can do all of this. However, all of that would be redundant, right? Like loading the same package several times and unloading it several times is redundant. An optimal plan won't do that. So if you find an optimal red-black plan, it's going to be a real plan. Okay? Anyway, I hope this gives you a bit of an intuition. The interesting observation is it was enough to unrelax, to paint black a single variable in order to fix the whole problem here. Okay? Yes, please. I'm going to get to this question in 5 minutes. Yes? Same question. Okay, wonderful. Good question. I'm not going to answer this one in this talk, but happy to take it offline or talk about it later. Let me first get through this. We can discuss this at the end if you want. Okay, I already told you about this, and it's very simple to see. So we already said that if all variables are black, I'm here. Trivial question, so that's it. I'm just going to always do that. All variables black, and I'm done. Well, no, right? Why not? It's too expensive. Painting all variables black is just a way of saying solve the real problem. Okay, so that's nonsensical. So you have to choose the right variables somewhere here for the trade-off, and you just ask me how to do that. And I don't think I have the answer on the slide. Anyway. But before we can even think about how to choose the red variables, we need to think about which ones do we have to paint red. Why is this a relevant question? Well, if you paint everything black, computing the heuristic function is p-space hard. Okay, you don't want to have that. You want to have a polynomial time computable heuristic function, so the question ends up being, okay, how far do I have to travel in this direction? How many variables do I have to paint red so that I can solve the thing in polynomial time? Right? This is a hard constraint, algorithmic constraint on your design. You need to paint enough variables red so that you can actually solve the thing inside the heuristic function. Okay, wonderful. At this point, I'm getting back to your question, and this is sort of one thing I like to do. I give students like 2 minutes to think about this kind of thing, and then you can sort of, try to propose one of those 4 answers. So, well, I mean, C and D are obviously kind of nonsense, but you can choose between A and B. Okay. I'm going to give you 2 minutes to think about this. Feel free to discuss with your neighbors or make noise or otherwise just relax. to know about, or is this thing just broken? Okay, are you guys ready thinking? Can anybody give me an answer? What happens if I do the painting the other way around? Truck is red, packages are black. Is it A or B? Maybe let's vote. Who thinks it's A? Okay, who thinks it's B? Okay, who has no opinion? Okay, very good. Thanks for raising your hand on the last one. So the correct answer is B. Does somebody want to explain why it's B? That was a majority vote, so you want to elaborate, Silvan?
Well, due to H plus, we don't profit from having the package relaxed because we still need to load them and unload them. So that's exactly what happens when painting H plus in the first place.
Yes, so if you paint this guy here red and those guys here black, the question is, do you profit from painting the packages black? The answer is no. Intuitively, I mean, you said it more formally, but intuitively because they don't have to move back and forward anyway. If you're a package, all you're moving is, well, I'm now at A, now I'm in a truck, now I'm at G. That's it. End of story, right? I'm not moving back along this sequence at any point in time. So painting those black doesn't give you anything. However, painting the truck red, you lose the information you gained before, right? Now the truck doesn't have to move back, and so you end up with exactly the value of the lead relaxation. So it matters a lot which variables you paint red. So in that sense, the question here was a very good one. I mean, we got like 17 different methods in the paper. There's all sorts of heuristics you can use. Most of them perform pretty similar, unfortunately. But okay. So now, for the more technical stuff, I told you that, you know, you have to paint enough variables red so that the whole thing becomes tractable, polynomial time solvable. And now here's the bad news. And actually, we were not the first ones to actually make this definition and find out this result. There's a guy called Patrick Haslund, who did it years before us. He invented the definition, and then he proved this result, and then he dropped the whole thing. So what does this result say? It says, in general, finding a red-black plan is NP complete, even when having only a single black variable. So you paint a single variable black, the whole thing, you know, explodes. Here's the proof, and that's sort of like a nice thing. So what I just put at the blackboard is a very rough illustration of how you do like SAT reductions in planning. So you have a CNF formula with n variables, V1 to Vn, and you got clauses on them. How do you encode this in planning? Well, for each variable you can choose a value, and usually it's unknown, and then you are able, an action, this is an action, allows you to choose whether to set it to 0 or to 1. Okay. You have those actions for every variable, so at the end of this here, you have chosen the value assignment, the true value assignment to your variables. Then you can make simple actions that just verify that all the clauses have been satisfied. So it's trivial, it's very easy to encode. Now, let's paint this whole thing here red. Okay. Okay. So this doesn't mean I've eliminated all this, it just means I painted all of this red. Question to you, does the construction still work? Is this still NP equivalent? Like, do I still encode satisfiability of the formula that way? When painting all of this red, I mean, the answer is a clear no, but the question is why? What can go wrong? Yeah?
Well, we can satisfy different clauses with certain variables by just setting them to 0 and 1 at the same time.
0 and 1 at the same time, that's the point. When I said it's initially unknown and I said you need to choose 0 or 1, I meant one of them, right? I mean, this is a single directed transition. Once you've chosen to go from U to 0, you can't change back anymore. You've committed to setting the variable to 0. However, if I do this under delete relaxation, after going from u to 0, well, I'm also still at u, so I can just as well go to 1. So if you do this in delete relaxation, you can assign any one of those variables 2 values if you so wish, and then of course, you know, it doesn't encode satisfiability anymore. Now, we have to fix this by introducing a single black variable, and then we have re-established, and that's the proof of this result, right? If I can fix this by adding a single black variable, then I've proved the theorem. And here's the interesting question to you guys. Do you see which variable I need to add to fix this? How can we do this? Problem is that, you know, in the delete relaxation, you know, can just assign 2 values to the same variable. How do I prevent this from happening? Okay. Unless I see any ideas lighting up for yes? 2 variables for each. That wouldn't fix the problem because, I mean, if you have 2 variables instead of 1, then you can set both of them independently, basically. And also, you need to fix this with a single black variable. So you're not allowed to introduce a black variable for each of those. If I was allowed to introduce n black variables, I would just make all of those black and the problem would be solved. But I'm not allowed to do this. I need 1 black variable. Okay, we don't have so much time. It's sort of a cute trick. Not so easy to see in 2 minutes, especially if this is the first day you even hear about all this stuff. So what you can do is an index variable. Let's call it vi, small I, because it's an index. Okay, the values of this variable, and well, you can't see this anymore. Let's look at this. They range between 1 and n. Right, so it has a finite range of values. I can change the choose the values 1 to n. Do you guys still see this back there? Do I need to move the... So this is the variable I introduced. And how does it behave? Well, it always points, its value indicates the variable whose value I'm being allowed to set at the current point in time. Okay, so initially the value is 1, which means that this guy is now allowed to move, to change its value, to pick its value. Now, when this guy commits to picking a value, like for example 0, as a side effect, that action increments the index. Okay, so now, after going from here to here, after I've decided to set v1 to 0, the index is incremented and it now points to the next variable. And now this guy can't move anymore, it's stabilized. Okay, so in this way I prevent those variables from cheating, from taking 2 values, and then the whole thing is fixed, and therefore this construction here proves the hardness result on the slide. Okay, wonderful. So like I said, Patrick Haslum did all this years before we did it, and then he proved this result and dropped the whole thing, because if you can't even paint a single variable black, it's hopeless, right? Let's forget about it. Anybody agrees on that? Should we just drop the whole thing? Does somebody see how to fix this? Any ideas? So does this result mean that red-black planning is just hopeless? Well, obviously it isn't, because I got more slides on it, but why is it not hopeless? Well, this result here holds in full general, right? Like, I'm not making any restrictions on the planning task. If you consider all possible planning tasks, for example, this one here, then, you know, you're out of luck. However, what if we do impose restrictions? You know, we got a large degree of freedom here. We're free to pick which variables to paint red. Now the question is, okay, can we paint them red in such a way that the structure of the remaining things that are black makes it easy to solve, right? So the question is, can we do this? I mean, it's sort of okay to require structural restrictions, because it doesn't mean that the input has to satisfy them. It just means that we have to be able to select a set of red variables so that they're satisfied. Okay, and here are the restrictions. Please don't read this definition. The causal graph is basically a graph over the state variables, where there's an edge between 2 state variables if they depend on each other, right? Intuitively, each package, or like this here is a variable that encodes the location of package A, and that depends on the truck because, well, intuitive packages depend on the truck, right? For a package to be able to move, the truck needs to move first. Okay, now, if you paint just the truck black, then this is what the causal graph looks like. Okay, so there are red parts, there is a black part. And the thing is that in the black part here, there's only a single variable. So in particular, there are no dependencies between black variables, because here trivially there's only a single one. More generally, the structure we're identifying is that where there are no dependencies between the black variables. Like each black variable can basically move on its own. It only depends on red variables. Okay, that's part one. Part two is invertibility. So again, let's just look at the example. This here is the so-called domain transition graph of the truck variable. This is just a graph over the possible values of the variable and how it can change between them. And for the truck, this just looks like, okay, you can move from G to A and back, from G to B and back, and so forth. And this is invertible because the truck can always go both ways. Okay, just to illustrate this definition a little bit more, can you think about what the domain transition graph for a package looks like? So, yeah, let's take package A. What is the domain transition graph? Did you want to specify?
Yeah, so it should have the different locations where it could be.
Mm-hmm.
So the truck.
A, B, C, D, and G, I think they were called, right? Mm-hmm. Okay. And?
Right, and so I guess the pickup actions allow any of the locations to put out with truck location?
I don't have a truck value here yet. I have 5 locations, A, B, C, D, and G. A, B, C, D, and G, yes, those are the locations. There's one value missing, namely the truck, right? So this is where the package can be, at any one of the locations or in the truck. Okay, how do you change between those?
Pickup action will put it from a location onto the truck.
Yes, and that works from any location, right? So this is like a pickup action. And then the drop actions just do the thing vice versa. Right? So here you also see the path the package is navigating, like I said before. You start at A, you're being loaded into the truck, and then you're being unloaded in G. So this is like a solution path from the point of view. So this is what the world like from the point of view of the package. But anyway, we got invertibility. And then what I like to call the SMS theorem is this one here. So if we have those two conditions, the black causal graph doesn't contain any arcs, and all the black variables are invertible, then we can find a red-black plan in polynomial time. More specifically, if you give me a relaxed plan, then I can transform the relaxed plan, the fully delete relaxed plan, into a red-black plan in polynomial time. Okay, I'm not sure I wanna have time to talk about some of the ideas. So, well, okay, let me give the intuition is the following. Just deliberating whether to use my slides to just explain like that. Okay, let me try to stick to the slides a bit more. So the idea is that this polynomial time algorithm that we need to design is called relaxed plan repair. So what we're going to do is to take as input a delete relaxed plan, and then you just process the delete relaxed plan step by step, and in each step you check whether the precondition of the action is satisfied. And this might not be the case for the black variables. We're going to see the example in a moment. So it can be possible that the black variable is not where it should be. The question is, can we fix that? Can we move the black variable where it belongs? And that's where those two preconditions of the theorem come in, prerequisites of the theorem. The first is the black variable doesn't depend on any other black variables. This means that I can move it without having to worry that something goes wrong for other black variables because there are no direct dependencies to those. Second, I know that this graph is invertible, so this basically means wherever the black variable is now, it can move everywhere else, wherever it needs to be. Right? If the black variable is now here, but it should be here to satisfy the precondition, well, I can move from here to there. And I can do this for any pair of nodes in this graph here. Okay, so the black variable can move on its own without interfering with anything else, first. And second, wherever it is, it can move anywhere else. And so whenever I encounter an unsatisfied black precondition in my relaxed plan, I can just take this black variable, move it where it belongs, and proceed. Okay? And at the end, I'm going to have a red-black plan. Okay, and this implies trivially, basically, that I have a complete and sound and efficient red-black planning procedure. I generate a delete relaxed plan. If no delete relaxed plan exists, I can stop because I know no red-black plan can exist either. If a delete relaxed plan exists, I transform it into red-black plan, end of story. So I can just put this more complex machinery inside the heuristic function, then I have something that gives me estimates that are more accurate than those of delete relaxation alone. Good. This is sort of just a joke. I mean, I wrote this from a train, and WhatsApp wasn't invented at the time, so it took me 3 SMSs to write the proof. What's interesting about this for robotics, I think, is that this kind of structure here is fairly typical. Like, you can think of these variables here as clients, like there are tasks the robot should accomplish, and this here is the position of the robot. And it's okay to have 100 robots, so long as one robot doesn't need to carry the other robot or something like that. So long as the robots move independently, like each of them can move on its own, you will have a structure that looks more or less like that, and you can use this heuristic function, and it's going to account for the robot moves. So when you pick the red variables, you're just going to have to make sure to isolate all the black variables from each other by a layer of red variables. Okay, good. This is the algorithm. Obviously, I'm not going to read you through the pseudocode. I would like to briefly show the example from before. Okay, so our input is the relaxed plan. Now we go through this step by step, and we try to repair it into red-black plan. Good. The first action, drive from G to A, we can just apply, and it works. Right? Now the next action the relaxed plan wants us to execute is to drive from here to here. Is to drive from here to here. That doesn't work, right? This action has a black precondition, the truck being here, that is not satisfied. So we need to repair the precondition. How do we do that? Well, we just drive there. Okay, now we repaired the black precondition, we can execute the action. Done. Next action comes up in the relaxed plan, wants us to drive from here to here. We need to repair the black precondition by going to here, and then we do it. Action process. So you see down here the relaxed plan is getting smaller and smaller. I'm just processing the actions one after the next. Now I want to go from G to D. Not possible. Repair the precondition. Apply it. Done. Okay. Now the load actions come up. Now I should load package A over here. Well, I can't do that because I'm here, but I can repair the black precondition by driving there, and now I load. Okay. Done. Now I need to load this guy, and now it gets repetitive, right? I repair the black precondition. I load. Now I should load this package here, repair the black precondition, do that. Last loading action, repair the black precondition, load. Okay, next I should unload at this position here. Again, I repair the black precondition, and now the next 4 actions I can just apply as they are, and now I'm done. Okay? Question to you. Does what I've just shown you yield an accurate heuristic function? What do you think? It is quite instructive when thinking about this to go back over this illustration here and not explaining anything and just letting you watch what the truck is doing. Okay, don't watch anything else on the slide, just watch this here and watch what the truck is doing. Does that make sense? Is that how you would do it? No, it's not, right? Why wouldn't you do it? All those useless drive actions at the beginning, right? At the beginning, I'm just going here. Sorry, not far enough. At the beginning, I'm just going here, and then I'm going back without doing anything. That's just stupid, right? So I drive across the whole map. I don't actually do anything. And then when the load actions come up, finally I realize, I have to be here again, and I load something. And this is not a coincidence. Unfortunately, it's actually systematic. So when we first implemented this heuristic, we thought, hooray, it's going to be great. And then it was total rubbish. And analyzing it, we found that, well, what a delete relaxed plan usually and systematically and typically does is, well, first, drive the vehicle across the total map, across the entire map. Those actions here are scheduled on my slide not in an adversarial way because I like to kill the algorithm. That's what happens in reality. That's what relaxed plans do, right? Due to the way we generate them, we don't need to go into the specifics, but that's what typically happens. If there is some sort of vehicle that moves around the map, first it goes everywhere and then it does something. Now when you repair this, the upshot is that, well, first you go everywhere and you don't actually do anything, and then when the actual things you want to do come up, you have to do the same thing over again. So it's a really dramatic overestimation. I mean, it's of course a bit of a gray answer. It's not a clear black or white, but it does yield a lot of overestimation, and in many domains it's detrimental. The good news is that this is possible. It's possible to fix that, and we've written more. We've designed more complex algorithms that are able to do that. Okay, and with this, I'm going to stop the discussion of this here and head into the last section of the talk. Are there any more questions on this? Should I try to answer your question how to select the red variable still, or? Pardon?
Give some idea about it.
Okay, so the way we do it is basically just we look at the planning task. We can sort of, we can create the causal graph very easily. So this graph here is something you produce in very little time, few split seconds. You can create this graph for each variable in very little time and check whether they are invertible. That's the first thing you do. And then you just go over the task. Initially, all variables are black, and then you just paint variables red until the condition of the theorem is satisfied. So basically, if in a black Hausser graph you do have neighboring black variables still, or if some black variable is not invertible, then you pick one more variable to paint red. How do you pick it? Well, if the variable is not invertible, you need to paint it red anyway, because otherwise you'll never be able to achieve this prerequisite. The first thing you do is paint all non-invertible variables red. Then if you still have direct dependencies between black variables, you need to pick one of them to paint red. How do you do this? Well, you try to paint the least important variable red. How do you figure out what is an important variable? Well, you create a relaxed plan, and then you see how often that variable moves back and forward. And if it moves back and forward very little, it seems a better candidate to paint red. Okay? Good. Any other questions on this? Yes? That's a very good question. In this formalism here, I don't actually have any negative preconditions. It doesn't allow this kind of thing. In the logic-based formalisms I've shown you, they are allowed. And the way you handle them in the delete relaxation is the easiest way to explain it, and the classical way to do it is by compiling away negative preconditions. You introduce a second variable. If you have a variable A, you introduce a variable not A, and just modify the action so that not A is true whenever A is false and vice versa. And then you can apply the same thing. Okay, so that's how people invented it. You can basically, negative preconditions can be compiled away. And then you apply the delete relaxation. If you think a little bit about this, the upshot of doing this is actually exactly what I've shown you on this slide here. Namely, this form here. So the upshot of this is that if you have Boolean variables only like in traditional logic-based AI, like propositions, they can be true or false. If you have those two separate variables, one encodes true, one encodes false, the upshot is that you're just pretending that you can make a variable true and false independently of each other, which is the same as saying you can accumulate those true values. Okay? So the definition I've given you here is a definition where all of this machinery has already been replaced by a more general definition. Initially when people invented the delete relaxation, and then, the question we were facing is, okay, so how do you apply this to some formalism like model checking or whatever that doesn't actually have negative effects, that doesn't have this kind of thing? How do you ignore deletes when there aren't any? And the answer is that, well, actually what this does is make state variables accumulate their values rather than switch between them. And that is a simple idea or explanation that you can apply anywhere. I can do this in timed automata. I've actually done it. Right? Automata also can be formalized as state variables. They can accumulate their values, sure. Right? So this is like the more general formulation I've given you. Okay, any other questions? Good. So in the remaining 10 minutes of this talk, I believe, right? It's going to be relatively easy listening. I'm just going to shoot some ideas at you that I think are really cool and that remain cool even if you don't want to commit to Pddl style planning. Okay, first one is if I had to pick just one idea developed in the heuristic search planning community and say this is the most important one, this would be it. Or the one that generalizes most smoothly to other areas. So let's look at the simple puzzle here. Question, usually in practice you don't have just one heuristic, you have several of them. The question is how to combine those. This is something that has occupied the heuristic search community beyond planning quite a bit. Ideally you want to be able to sum up the lower bounds. Question of course is the sum still a lower bound? What's the answer to this question here? Is the sum of the two heuristics still admissible? So this is like a standard relaxation of the 15 puzzle where you basically ignore all but a subset of the tiles. Can you sum these two up here? What do you think? Is it still a lower bound? How have I chosen the tiles that I ignore on the two sides? Is there any tile that appears in both of those? Well, there isn't, right? They are disjoint. So the sum is admissible. So there's a series of papers written about this kind of thing by Richard Korf and other people. So the famous sort of admissible summed heuristics. Okay, they're orthogonal, they're independent, you can sum them up. Okay, great. Now I've changed this a little bit. I've introduced the 3 here. Can I now still sum this up? No, I can, right? The 3 is on both sides. So if you have a relaxed solution here and a relaxed solution there, both of them might move the same tile, number 3, and those moves would be accounted for on both sides, and therefore there might be double counting, and so it's not a lower bound anymore. Now, that's where the whole story stopped for Richard Korf and many others for about a decade, and then there was a project meeting in 2006 where I was sort of blabbering to other people about how great orthogonal heuristic functions are. And then some guy asked the following question. Okay, fine, it overcounts, it's not invisible anymore, but what if I just, said that moving the 3 here costs only 0.5 instead of 1, and moving it here also costs only 0.5 instead of 1? Can I then sum the 2 guys up? Well, I can, right? I mean, the moves of the 3 might be accounted for on both sides. However, if I, artificially reduce the cost, if there is double counting, no worries, because 0.5 plus 0.5 is 1. So it's not going to be a problem. Right? So this is like the simplest possible way to actually get rid of double counting. At the time, I just sort of scratched my head and thought, yeah, I guess it can be done. It looks like a bit of a hack, and then I forgot all about it. Until like 3 years later, somebody wrote a paper calling this cost partitioning and formulating it in a very general way. So you're given a planning task here, but it can be anything. As long as you're solving some problem that involves reachability in a transition system, you can do this. Let's say you have an ensemble of lower bounds, h1 to hn, and the transitions in your systems, transition systems have costs associated with them. You can just partition the costs of the transition labels, in our cases actions, but transition labels can be anything, so long as they have some cost. You can partition the cost across and different transition systems. You can apply lower bound I to transition system I and sum the whole thing up. It's going to be a lower bound. Okay, so this is super general. It vastly generalizes the results that have been established for a decade in the single agent Zerf community. You can do this with literally anything. Okay, wonderful. What is the problem? Well, you have to find this partitioning here, right? Action costs are usually continuous functions, and action cost is a real number. Let's say if you have 10,000 different actions, 10,000 different transition labels, you need to choose how to partition the cost of each label across your n heuristic functions. Obviously, this is it sounds like an impossible problem, right? There's actually an infinity of choices how to partition the cost. How do you solve this problem? Well, it turns out that for particular heuristic functions, you can actually do this in polynomial time. And you can, in polynomial time, find the best possible cost partitioning, the one that maximizes the resulting lower bound. The resulting lower bound is the sum of heuristic functions. You can actually maximize the lower bound, get the best possible lower bound achievable given this ensemble of heuristics in polynomial time by encoding the whole thing as an LP. Okay? Obviously, this can't be done for arbitrary lower bounds, but it can be done for large classes of lower bounds. For example, anything called an abstraction heuristic, which is the very classical way of approximating transition systems. You just superimpose an equivalence relation over the transition system. Okay, if you're interested in all of this, you can read the literature. Next cool idea I'm going to skip over for lack of time. Sorry about that. But you can actually approximate H plus very closely. I previously told you that we got this H1, which is a lower bound on H plus, but is really, really bad. Turns out we can basically get H plus with a polynomial time approximation. From this paper here by Helmut and Domschlag, ICAPS 2009, but I'm going to leave it at that. You might have heard about these alpha something things coming out of London in the recent years. I've also heard about them, so what do I think about that? Well, to me, this is basically computing a heuristic function with different methods, right? So, we were always going on about taking a model of the world and relaxing it in some automatic way and computing the heuristic value. Here, just learning the heuristic estimation from data. One thing that can be done in Go and chess, but it cannot be done in planning here is assuming a fixed input size, right? So the game board has a fixed size. In planning, we don't have that. I previously showed you this Pddl stuff here, right? Still got it here. So if you look at the domain file in elevator control, it's always the same. Like no matter which elevators you're controlling, the predicates and the action schemas are always the same. However, you do get different universes, right? Different initial state, different goals, and different universes, right? If you do this in a different building, there's going to be a different number of floors. If there's 17 passengers, it's different having 27 passengers. So the input size is not constant. The question is, can you learn something that generalizes across all possible problem files? That's what they call per domain learning in planning. like offline, at learning time, you learn something that later on you use on different tasks that have a different set of passengers, different set of floors. The only thing you can assume to be constant are the action schemas and the predicates. So the question is, can we do something like that with neural networks? And that's the cool part. I mean, why this here is cool, the answer is actually yes. Or at least the first method to actually do this kind of thing exists. And what's also cool about this, the guy who did it, Sam Toyer, was a student at this summer school last year, and he actually published this work in between. So I'm now reporting about work that like one of you in the previous year's edition has done in between the two schools. So let's see if the same thing can happen next year again, if there's going to be a third summer school. Okay, the basic idea is that you learn the weights in the neural network for the things that remain constant in the domain. And what are those? Well, it's always the same action schemas and the same predicates. So that's something you know will remain fixed. You learn the weights on that level, and then you share them for all ground actions and ground facts based on those schemas and predicates. And then you have to deal with the fact that like there will be more neurons for larger problem tasks in the domain, and you deal with that by pooling. You just use a simple maximization function. And ta-da, you can train a neural network on small instances and apply it to much larger ones later on. And it actually works in some domains. Intuitively, those where like learning a single simple trick enables you to solve everything in the domain. For example, in the classical tire world, the task is to exchange a flat tire. So you have to like hump up the car. I don't know how to say this in English, right? You know, undo the screws, take off the old tire, put on a new tire, you know, do the screws and do the whole thing back again, and then you've done. How does this domain scale? Well, in larger tasks, you don't have to replace just one tire, but 1, 2, 3, 4, 5, 6, 7, 8, 9 tires, right? Or as many tires as you want. Of course, this is a bit nonsensical, right? Nobody has 17 flat tires on the same car at the same time. However, if you learn how to do one tire, you can do 17 tires. And the neural network manages to do this, okay? So that's the kind of thing this can do as of now. So it's a bit limited, of course, more. If the domain changes in more general ways, it's unable to do this kind of thing, but they're working on it. Good, almost done. So this here is just a section where I briefly point to interesting topics to do research about in planning when you're interested in applying planning to robotics. Okay, so I don't know for how many of you this profile is actually a fit, but you know. So this is future work that's relevant for planning researchers in the application of robotics. One thing is real-time search, right? In the real world, there's usually very little opportunity to just stand around and think. Right? Usually you need to decide like within seconds or maybe minutes or maybe hours tops if it's a really complex decision. But standard heuristic search doesn't actually support this. So you need to investigate methods that are actually, conduct the search in a way that is aware of how much time there's left to think. Right? Imagine you're solving the Rubik's Cube. Well, you're trying to solve the Rubik's Cube. There's a difference, right? If you only have 30 seconds left, you're going to think differently than if you have 2 hours left, right? If you have 2 hours left, you're going to think much more deeply. If you have 30 seconds left, you're going to think more broadly and just try to get an idea of what might be a good direction and then go ahead. Right? And the current search methods we have are just unable to do this. So the question is, how do we enable them to do that? It's of course it's a nascent research area. There has been some research, but we're far from having solved this in a meaningful way. I'm going to skip this over. Explanation, of course, everybody is talking about it. In principle, like model-based methods give you the opportunity to explain stuff, but we haven't really figured out how to do it yet. For example, one question we have no answer to is if the user, like the robot suggests, or the computer in more general, suggests to the human operator a plan. The operator might ask, well, why this plan, why not this other plan, right? It's something people tend to do, asking those nasty questions. Why should I go to A? I'd rather go to B. Why do you want me to go to A instead? And we have no way of supporting answers to this kind of question right now. I had the same slide on last year. I mean, in the meantime, something has changed. I've written a project proposal, how this might be done. So that's what you do at my age. You don't write a paper, you write a proposal, and then you hire someone who writes a paper. Not sure this is very useful, but anyway, so there might be stuff forthcoming in the next 1, 2, 3 years. Finally, the deep learning, of course, is something that occupies us all. I've already talked about this way of using it, so try to use it as a tool for efficient planning. I think it's also interesting the other way around. I mean, I do think that model-based methods have a role to play in this world where people just use data to learn everything. And what's the role they have to play? Well, you know, safeguard and explain the behavior of the system. So safeguarding just means, okay, instead of just executing whatever the classifier suggests you to do, you know, do a look-ahead search and, you know, figure out what's actually going to happen later on if you follow that suggestion. So that's pretty straightforward. They even do this in AlphaGo, right? If you just let the neural network play, it's not going to achieve word-level performance. You also need the Monte Carlo tree search in order to figure out what's going to happen if you go somewhere. The other thing I've been thinking about lately is to use models for validation of a learned policy. So, you know, you can, you know, like at design time, you're not yet acting, you're at design time, you've learned the policy, you just want to figure out how will it behave under different circumstances. Can I validate this? Can I verify that it's not going to, you know, lead me into a fatal situation at any point? And so that's, I think, a big role that model-based methods have to play in this context. And that's all I wanted to say. Last thing is, if you became interested in some of this, but you know, are a bit scared of reading all those papers here, there's something much easier you can read, namely my lecture slides, which explain most of this in a fairly simple way. And I've actually got like links behind each of those here. So you can just click on this and, you know, look at it. That's it. Thanks for your attention. Okay, are there any questions? Or maybe we should just cut it off here, go into the coffee break. I'll be around the whole day, so, you know, speak to me later on if you want to. Okay, enjoy.
We will return at 10:30.